Okay, so this one is going to integrate a definite integral here from 1 to 4 x cubed natural log of x dx. So what I'm going to do here is I'm going to let the u be the natural log of x, so that's going to be u, and then the dv is going to be the x cubed times dx. So you can see here I let u equal natural log of x, so that makes du be 1 over x dx, and then dv is x cubed dx, and when you integrate x cubed dx to get v, you get x to the 4th over 4. So now this integral, remember, is now going to equal uv, so that would be uv would be the natural log of x times v, which is x to the 4th over 4. So that's x to the 4th times natural log of x all over 4, and then minus the integral of v du. So the v is x to the 4th over 4, and the du is 1 over x dx. Okay, so now let's clean that up a little bit. X to the 4th over x is x cubed. So I've got x cubed there, and I factored the 1/4 outside of the integral. And of course I copied the first term down, the uv that I had right there. Now what I've got to do now is I've got to integrate x cubed dx, and we know how to do that with the power rule. If you integrate x cubed dx, that's going to be x to the 4th over 4, and remember I'm multiplying it by a 4th, so a 4th times x to the 4th over 4 would be x to the 4th over 16. Okay, so now there's my function, and I've got to integrate that function from x equal 1 to x equal 4. So basically here, once you have the function, you just apply the fundamental theorem of calculus. So plugging 4 in, I get 4 to the 4th times natural log of 4 divided by 4, and then minus 4 to the 4th over 16. And then minus, now evaluate this at 1, I have 1 to the 4th times the natural log of 1 over 4 minus 1 to the 4th over 16. Okay, well, 4 to the 4th divided by 4 is just 4 cubed, so that's going to give me 64 times natural log of 4. And then 4 to the 4th divided by 16, that would just be 4 squared, which is 16. So that's 64 natural log of 4 minus 16. Now the good news here is natural log of 1 is 0, so I'm just going to have 1 times 0, so that's just going to give me 0 there, and then minus 1/16 there. Now, simplifying this, I get 64 natural log of 4 minus 16, and then since I'm subtracting a negative, I'd have plus 1/16. And then if you needed a value, a decimal value, you could just plug it in your calculator to figure it out. I got 72.79 rounded to 2 decimals. So that's the answer. Now, if you didn't want the decimal, you could combine minus 16 and plus 1/16, and that way you could combine those two and get a fraction. But that's your answer there. Now, freeze the video here if you like and work on these problems. I'm going to give you a hint. I've given you 3 practice problems here, and I'm going to give you some hints here. Now on this first one, I'm not really sure if one method works better than the other, but one way you could do is you could let u be x squared, then dv would be e to the 7th dx, and then that way you could get du would be 2x dx, and then v, by integrating this, you would get e to the 7x divided by 7 times dx. Or you might try it the other way around. Maybe you let u equal e to the 7x, and then dv would be the x squared dx. It might work either way, but this is how I would start first time. Now on number 2, I would let u be the natural log of x, remember, because you can't really integrate that nicely. So let's let the u be that so that I can just take the derivative of it to get du. And then let dv be the x squared dx. And then you can integrate that and get x cubed over 3 times dx. Okay, actually I'm telling you wrong here. You don't get the dx there. When you integrate this, you just get the function x cubed over 3. So that's my bad right there. Okay. Oops, that's fine. Okay, so I got it right down here. Okay. But anyway, you get x cubed over 3 when you integrate. And then here, for this one, I would let u equal x, and then I would let dv be e to the minus x dx, and then when you integrate, when you differentiate to get du, you get du equals dx, and then when you integrate to get v, you get v equals minus e to the minus x. And then of course, after you integrate these, make sure you apply the fundamental theorem of calculus and try to get the same answer I got. Okay, I won't work all of these, but I'll show you how to get started on these. The first one is x cosine x dx. So if you let u be the x portion of that integral and let dv be the cosine x dx, then du would simply be dx, and when you integrate both sides, v would simply be sine x. And then that integral would be uv, which would be x sine x, minus the integral of v du, which would be sine x times dx. And you know how to integrate sine x. That's just going to be minus cosine x. So when you get a minus cosine x with a minus already in front of the integral, that's going to make that a plus cosine x. So bring down the x sine x, the cosine x, and then obviously your plus c. Okay, now on this one, at first you might not think there's anything you can do here because all you see is natural log of x dx. But you could let u equal natural log of x, and then that way du would be 1 over x dx. And then you could just let dv be dx. And then when you integrate both sides, there v would be x. So if you do the uv, you would get a natural log of x times x, which I'm just going to write as x times natural log of x, minus the integral of v du, and v is x, and du is 1 over x dx, and x times 1 over x is just 1, so you end up in this integral with just dx, and when you integrate dx, you just get x. So I bring down the x natural log of x, and then I have the minus x from this integral, and then of course plus your constant. And so now you have a formula for integrating the natural log function. Remember I told you earlier we didn't have that, but now we do. Sometimes you have to integrate more than once using this parts method, so let me show you how that works. On this right here, x squared e to the x dx, I'm going to let u be x squared, and then I'll let e to the x dx be the dv. So if u is x squared, then you can see that du is 2x dx, and then if you integrate this, you'll just get v equal e to the x. So when we integrate, when we apply the formula, we get uv, which is x squared e to the x, minus the integral 2x e to the x dx. Okay, so now this is another one here that I'm going to have to apply parts to this integral to integrate. So let's do a second integration for this integral here, 2x e to the x dx. So let's see what I can do here. Why don't I just let the u be the 2x, and then let v be e to the x dx again, or dv be e to the x dx again. Well, then when you integrate, differentiate this, you get du equals 2dx, and when you integrate here, you get v is e to the x. So now we can figure out what this integral equals. It's going to equal uv, which would be 2x times e to the x, minus the integral of v du, and v du would be e to the x times 2x. So you would get, e to the x times 2 dx, so you would get 2 e to the x dx. And since we know how to integrate e to the x, we can just write this integral as 2 e to the x, and of course we have a minus in front of the integral. So that would be 2x e to the x minus 2 e to the x plus a constant. Okay, so now, since I know what this integral equals, then I can actually replace it. I can replace this integral with what I got over here. And remember, I'm subtracting, so when I plug this in right here, I've got to distribute the minus through, so that instead of 2x e to the x, I'll have minus 2x e to the x. Instead of minus 2 e to the x, I'll have plus 2 e to the x. And then, of course, just throw your constant in at the end. And so now you have all of your terms. This problem introduces something we call the foldback rule, and I'll show you how it works. Here I'm going to let u be e to the x, and I'm going to let du be cosine x dx. or dv, I'm sorry, dv cosine x dx. Now the derivative of u would just be e to the x, so du would be e to the x dx, and then when you integrate both sides here you get v equals sine x. So I can write this as uv, which would be e to the x sine x, minus the integral of v du, which would be sine x times e to the x dx. And then here, to evaluate this integral, I need to apply the parts method again for this integral. So let's see how we can do that integral. So here I'm going to let u be e to the x, and I'm going to let dv be sine x dx. And now applying to that integral, I'll get e to the x cosine x dx. That's going to equal, let's see here. Okay, let me show you what I did. Now this is the original integral, e to the x cosine x dx. And that equaled, if you go back up here, we got this as the first term, e to the x sine x. So there's that. And then minus this integral. So I've got to replace this integral with, and I'm going to just put it all in brackets so I can distribute the minus through. So this integral, remember, from here, this second parts integration, I can write it as uv, which would be e to the x times minus cosine x, so that would be minus e to the x cosine x, and then minus the integral of v du. And since v is minus cosine x and du is e to the x dx, I get minus e to the x cosine x dx. Okay, now let me simplify this a little more. So bring this down and you get e to the x sine x, and you get e to the cosine x. And then here you get minus, well, you distribute the minus, you get minus and minus, so it's going to be plus. Let's see, I'm sorry, there's three minuses, because you got a minus here, you got a minus here, and you got a minus here. So it's actually going to be minus the integral, this integral. Okay, but notice something, this integral is the same as this integral. So if I were to add that integral to both sides of the equation, it would cancel here and then give me two of these integrals over here. So I'd have two of those integrals, and then two of those integrals would equal this sum, the two terms I was left with, and then I could divide both sides by 2, and when I divide both sides by 2, I get my solution for the integral here. And that's just going to be e to the x sine x over 2 plus e to the x cosine x over 2, and then at the end plus the constant. I've got one more video I want to do on this section. I want to show you how to do this using what's called tabular integration, and also on the next video I've got an application that we'll look at. So you're still not finished with this section, so I'm still going to show you some more tricks in the next video. So make sure you see the third video for this section.